Hi, welcome to our presentation of the paper CyIE Cylinder Embeddings for Multi-Hop Reasoning over Knowledge Graphs. We are Chau, Nguyen, Tim French, Wei Liu, and Michael Stewart. We are from the ARC Training Center for Transforming Maintenance through Data Science, Natural Technical Processing Group, and School of Physics, Mathematics, and Computing at the University of Western Australia. We are working on the task of answering complex logical queries over knowledge graphs. The complex logical query can be represented using a computation graph. This query in the computation graph is to communicate with knowledge graph. For example, on your left is a complex logical query, and on your right, an example of the knowledge graph that the query interacts with. However, knowledge graphs in the real world are incomplete. And why incomplete knowledge graphs? Because there are missing links between some nodes. There is no guarantee that we have all true links between all nodes in knowledge graphs. Using conventional approach like subgraph matching cannot traverse missing links in this situation. So we come up with a question. Can we have another approach to answer the complex logical query? Recently, the query embeddings approach was shown to be effective in addressing this problem. The key idea of the query embeddings approach is to project entire entities and queries into a low-dimensional embedding space. This approach enables the model to predict the answer entities without the need of traversing the graph. To achieve the query embeddings, one of the most popular ways is first to rewrite the natural query into the first-order logic query. This is done by using a set of basic first-order logic operators. These operators are essential quantifier, conjunction, disjunction, and negation. The first-order logic query combines these symbolic operators, semantic entities, and relations extracted from the natural query. In this example, we can see that the first-order logic includes key information from the natural query. These are entities and relations under the combination of logical operators. And after having the first-order logic query, this query is then represented into the computation graph, as you can see here, where nodes represent entities, edges represent the relations or the logical connection between one-hop queries. Now let's look at the computation graph in details. For example, we have one hop query for the relation acted in film and another one hop query for the relation profession of with negator. The intersection operator combines these one hop queries and produces an intermediate entity or an embedded query. From this intermediate entity, given the relation has profession, keep the reasoning process to get the final embedded query. At this stage, the question is that what representation for nodes in the computation graph in machine-readable way and how to model the edges in this graph. In this work, we introduce cylinder embeddings approach to embed queries and entities. We represent queries into unbounded sector cylinder embeddings, where there is no parameterization for the radius of a sector cylinder embeddings. In general, there are three variables to represent sector cylinder embeddings in our approach: a semantic symmetric axis, an aperture, and a height. The semantic symmetric axis is the angle between the positive x-axis and the semantic center of the sector cylinder. The aperture is the angle between the upper and the lower bound of the sector cylinder, and the height of the sector cylinder. For the entities, we represent these into cylinder embeddings. Notice that there is no parameterization for the aperture, as this variable is not necessarily to model the entities. An entity is individually compared to query having more than one entity, and represent entities in this way can reduce space complexity during modeling the process. In summary, we embed the queries using a Cartesian product of sector cylinders, while we embed entities using a Cartesian product of cylinders. In short, we call the entire approach cylinder embeddings, or CyIE, compared to the only previous geometric models without high dimension. Now, let's look at the overview of the cylinder embeddings approach using the early example with the query. lists the professions of those who acted in the flash film that are not film director. Each node in the computation graph is represented using the cylinder embeddings approach. The embedding process starts with two anchor entities, splash film and film director, also known as source entities, highlighted by the blue regions. This process goes through the computation graph until getting the embedded query, highlighted by the green regions. The embedded query shortly represents the entire natural question above. At this stage, we show the embedding process of nodes in the computation graph to project queries and entities into the embedding space. However, we still need to find a way to model the relation projection operator and logical operators. These are the edges in the computation graph. Now, going to the modeling process for the edges in the computation graph, we have relation projection and the first-order logic operators, which map to the edges in the computation graph. Intuitively, inspired by the geometric shape of sector cylinders, the relation projection operation of a sector cylinder can be another sector cylinder. For modeling the conjunction operator, we consider the intersection of the sector cylinders. For modeling the disjunction operator, we consider the union of sector cylinders using disjunctive normal form. This is a disjunction of the conjunctive queries. For modeling the negator, we consider the closure complement of a sector cylinder. For example, the green region represents the output for each modeling process. So far, we have shown the embedding process of nodes and edges in the computation graph. Now, we'd like to recap the pipeline so we can see the entire process of embedding query again, starting from the first-order logic query, which is converted from the natural query. The first-order logic query is then transformed into a query in the computation graph. Finally, we apply the query embeddings approach, cylinder embeddings in particular, for representing nodes and edges to project query into this embedding space. Moving on to the optimization method. For training loss function, we want to minimize distance between the embedded query and positive answer, while we want to maximize the distance between the negative answers and the embedded query. To calculate the distance between answers and embedded query, we have three terms: for the outside distance, the inside distance, and a high distance. Putting it all together, we design experiments using large knowledge graphs. These are free-based and never-ending language learning, or also known as NEL. However, these large knowledge graphs are computationally expensive in space and time to pre-process data and train models. We therefore use subsets of these large knowledge graphs to have the three datasets for training models. These are Freebase 15K, FB 15K237 from Freebase, and NEL 995 from Never-Ending Language Learning. These datasets have around 1 million triples in total. We split each of these datasets into a training, validation, and test set. For generating logical query structures, there are 14 query structures in total. 10 structures are for the training process, and all is for the evaluation process. Here, we can see a brief illustration of those query structures for the training process and those query structures for the evaluation process. We feed the queries and their answers to train the CyIE model using the cylinder embeddings approach. For the results of answering negation queries, CyIE is on par with the best performing geometric-based model ConE. Notice that existing models, beta-E, ConE, CyIE, have not achieved a good coverage of performance in mean reciprocal rank at between 5.5% and 6.5%. However, for the results of answering union queries, CyIE was shown to be significantly more accurate than the previous geometric-based embeddings model ConE. Specifically, it's up to 12% improvement in queries to yield and up to 7% improvement in queries UP. For the results of answering non-negation queries, CyIE achieves significantly higher performance than baseline models. and we observe that these results are consistent using the three benchmarking datasets. These query syntaxes are the combination of projection operators with logical operators. Up to 6% improvement over coding on average, and specifically up to 14% improvement in query IP, intersection and projection queries, and up to 10% improvement in queries 2P or 2 projections. Here is an example from the model output for the query 2 projections, and another example from the model output in the query 2 intersections or 2I. In summary, we have demonstrated that a novel 3D geometric-based embeddings model, CyIE, for query embeddings approach. This model can handle a complex set of basic first-order logic queries for the answering complex logical queries over knowledge graphs. Results from experiments show promising capability of CyIE as a 3D geometric-based embeddings model to achieve the task of multi-hop reasoning. And CyIE can open research to further query embeddings methods using 3D shape to achieve the multi-hop reasoning task. Thank you for your listening.